So what do we make of stuff like this? Let me just grab this problem and we'll use it as a kind of a vehicle for talking about what this means. That looks weird. How come that's way up there? I don't know. Okay, so there's the function that we're looking at. And the question that we're asking ourselves is, what's the growth or decay factor? Okay, so this is exponential growth. Now, we haven't talked about this at all, and we're just going to get just a really brief introduction to it. We'll talk a lot more about it next year. Okay, when you have a function like this where it looks like y equals, now what's, instead of these and m's, the book uses, we'll make sure I use the same stuff that our book does. Not that it really matters. I don't know if you're going to look in this book, but I have to use A and B. Yeah, A and B to use. Yeah. Okay, that's what an exponential growth function or decay function looks like. That's an exponential function. Now the graph of those, this is when people talk about something, you know, people say, man, it's growing exponentially. What do they mean by that? I mean, doesn't that imply something about how fast it's changing? Someone says it's going exponential. I mean, that means it's just taking off, right? Well, this is what the graph looks like. If I graph an exponential function, it does that. The rate at which it grows is increasing at a steady rate. So it grows faster and faster and faster with time. Okay, you can see that curve climbs more and more steeply. And like I say, you'll look at this a lot more next year in more detail. But how do we describe that curve? Well, there's a couple important parts of this function. This is what we might call the initial value, or sometimes it's called the start value. So that's the value that it's starting off with. Now, this could be an example. We'll actually look, not today, we'll look at a couple problems that apply to like investments or something. This is maybe how much money we invest in the bank to begin with. That's the starting value. And this guy right here is what we call the growth or decay factor. If it's getting bigger, it's growth. If it's getting smaller, it's decay. Okay, and then this, the independent variable, is typically going to be like the number of years. If we're measuring an investment, how much money is in the bank every year, we leave it in the, where X is the number of years, that's going to make a prediction. So 20 years later, how much is going to be in our account? Okay, so this is, usually it's time. And it could be, could be years, could be weeks, who knows? If bacteria are growing, maybe it's hours, depending on the context of the problem. So all we're trying to do right here is identify what's the growth or decay factor. Well, what is it? I mean, if I match this function up to the template for an exponential function, what's A? That's a time sign, by the way. That's kind of an awkward time sign. But that's all that is that time sign. What's A? 4121. So the initial value of this function, who knows what it means, is 4,121. That's what we start off with. What's the growth factor? 2.42. So what that's telling us is that every time x increases, the size of this function is increasing by a factor of 2.42. So when x is 0, when it starts off, it's 4121. When x is 1, after, say, 1 year, we're going to multiply that initial value by 2.42 to the 1. So it increases by that much. After 2 years, when I put a 2 in, up there for x. 2.42 to the 2, isn't that just 2.42 times 2.42? So every time we add an x, we're just multiplying by an additional factor of 2.42, right? So if that number were a 2, instead of a 2.42, like if we had a function like this, let's say, y equals 10 times 2 to the x, well, we're starting off with a value of 10, and every time we increase x by 1, we're going to double what we had, right? So we start off with 10. After when x is 1, we get 20. When x is 2, we get 10 times 2 squared is 4, we get 40. When x is 3, we get 10 times 2 cubed, so that'd be 80. Every time it's going to double, right? So that growth factor really does mean that. It's a factor, and how much are we multiplying our amount by every increment of x? Time, could be weeks, could be days, like I say, it depends on the situation, okay? So in this case, the growth factor is just this, 2.42. Okay, that's it. All right, let's look at another one. Okay, this guy here. Same question. Let's make this bigger. Now the last one was clearly growth, right? Because it was getting bigger. What's the growth or decay factor here going to be? What's if we compare this to our function that we were just looking at, right? Y equals a times b to the x, where b is the growth or decay factor. What's the growth or decay factor here? 0.89. Okay, now what's going to happen if I multiply something by 0.89? Is it going to get bigger or smaller? It's going to get smaller. So do you suppose this is growth or decay? Decay. Now what's going to distinguish growth from decay? What number is going to be the boundary here between growth and decay then? 1. Sure. Anything bigger than 1 is going to be growth. Anything less than 1 is going to be decay. Okay? But the answer, they just want to know what's the growth or decay factor. Well, there it is. 0.89. Okay? All right. Okay, what's the initial value in this function up here? Yeah, 1647. Right? That's the initial value. Okay? The number that's being multiplied out in front, the constant that's being multiplied out in front. Okay? There it is. Okay, I got initial value. Good. Okay, next issue. Percent growth. That's a little different than decay factor. Now, we want to express this as a percent. We have to think of this just a little differently. So let me grab this one. Okay, now when we want to write something in terms of percent, we're going to tweak that last equation just a little bit. It's very simple, and it makes sense. And this is a really good thing to know because we like to talk about things in terms of percent growth. How much of you've heard stuff like this before? Let's say the economy, we'd like the economy to experience 4% growth rate or something like that, right? Or we want to invest our money in a fund that has greater than an 8% yield, meaning the growth rate's going to be bigger than 8% if we can in a long-term investment. You hear stuff like that all the time. Well, what's it mean? Okay, here's what it means. I'll make that a t instead of an x, so it reminds us that it's time. Now, instead of writing the growth factor as a b, we're going to change that to 1 plus or minus r, where r is the percent. Okay, that's the percent change. So the b, we're going to write this way. And this is the decimal equivalent of the percent. So what I mean by that is, let's take an example. What if we have the function y equals 10 times 1.15 to the t? Okay, now there's my growth factor, 1.15. If I write that in the form 1 plus something to the t, well, what's the something? 1.15 equals 1 plus what? 0.15, right? Plus 0.15, right? And so that is r, right? That's the rate. Now, that's as a decimal. If I turn that into a percent, what is that as a percent? 15, right? To turn something into a percent, I just multiply by 100. So it'd be, what would it be, if I scoot the decimal over 2 places then, I just get 15%, right? So then what is the, for the example I just gave you, if we want to know what is the percent growth or decay, well, it's growth, isn't it? Because 1.15 is bigger than 1. And R, written as a percent instead of a decimal, was 15. So that would have been 15% growth. Okay? What about the example they give us? If I take this B here, 2.21, that's B, and I write that in terms of R, what's R going to be that time? 1.21. Okay, so R equals 1.21. As a percent, what is that? 12 point. We're going to move it 2 places, right? Multiply by 100. That's good. That's all right. There you go. Okay, so yeah, so that'd be 121%. That's quite a bit, right? Now that makes sense, doesn't it? What would 100% growth be? If you had 100% growth, then every time, like every year, you would be increasing the amount you had in there by 100%, meaning whatever the value of the investment was. Say you had $100 in the bank, and you're making, somehow you're making 100% growth on that, then all 100% of that, or $100, you're getting back in addition to what you already had there, right? That's how much you're getting paid, 100% of what you already had in the bank. So what are you going to have after a year then? Twice as much. You have $200, right? Just 100% growth. Now, if it's 10% growth, you're only making 10% of that $100 in growth. You're only making $10. But this is pretty good. I mean, this, if you're making 121%, after a year, you would be making more money on the money that you have in the bank than you initially invested, right? That makes sense, though, because look at our growth factor. We're multiplying by more than 2. We're more than doubling what we had in the bank. Okay? Okay, one last example then, and I think we're good to go. So I want to look at one like that. Okay. It's just a little trickier here, so I want you to tell me now what is okay, so if this is my exponential function now, I want to know what's the percent growth or decay. What's B? Okay, so the growth or decay factor is growth or decay? Decay. So the decay factor, B, is 0.91. Now that's got to be equal to 1 minus plus or minus R, right? I mean, R in this case is going to be positive or negative. Negative. Yeah. What's R going to be? Ah, okay, good. If I take that equation, that's really a pretty easy one to solve, isn't it? We'll just make it a plus, and if it ends up being a negative sign, then so be it, right? If I subtract 1 from both sides, I get negative 0.9 equals R. So then what is R as a percent? Yeah. As a percent, it's just -9, isn't it? If I move the decimal 2 places. So the negative means decay. We're losing 9%. Okay? Make sense? Okay, that's a lot of stuff. All right. So we'll hit the lab tomorrow. Get a chance to work on things a little bit, and then we got one more day of this, and then we're in the lab for the duration.